What if I told you that the entire digital world, your phone in your pocket, the computer on your desk, the vast, invisible network of the internet itself, is all built on a convenient lie? Not a malicious lie, but a choice. A practical, simple, decades-old decision that set us on a path so deep we forgot there were ever other roads to take. We live in a world of 0 and 1, on and off, true and false. It's the bedrock of our reality, but it was never meant to be the only way. Today, we're going to pull back the curtain on a ghost in the machine, a forgotten language of computation that was faster, more elegant, and more efficient. A language that is now, out of sheer necessity, clawing its way back from the grave. This is the story of the binary empire, the lost ternary revolution, and the battle for the future of energy, AI, and everything in between. The story of modern computing doesn't begin with a flash of genius declaring binary code as the one true path. It begins, as most foundational technologies do, with a compromise. In the flickering, vacuum tube dawn of the digital age, engineers faced a simple, physical problem. How do you reliably represent information in a machine prone to voltage fluctuations and electrical noise? The easiest, most robust answer was to use just two states. A high voltage could be a 1, and a low voltage could be a 0. It was a brute force solution. It was stable. It was easy to build and easy to debug. Think of it like a light switch. It's either on or it's off. There's very little room for ambiguity. This decision, born of practicality, became dogma. It cascaded through every layer of the emerging digital ecosystem. The first programming languages were designed to speak in ones and zeros. The first microprocessors were architected to think in binary. Universities began teaching this as the fundamental truth of computation. An entire global industry, from silicon foundries in California to software giants in Redmond, was built on this simple two-state premise. It was the technological equivalent of deciding that all cars worldwide would run on a single type of fuel. It wasn't necessarily the most efficient fuel, but because everyone agreed to use it, the infrastructure, the gas stations, the refineries, the mechanics grew around it, making any alternative almost unthinkable. But now, deep within the humming data centers that power our modern world, the limitations of that initial choice are becoming a crisis. The demand for computation, driven by artificial intelligence, is growing exponentially, and so is its thirst for energy. The binary system, once our reliable workhorse, is showing its age. And from the shadows of history, a provocative question re-emerges. What if there was a better way? What if, instead of just on and off, we had a third option? This is the provocation of the ternary system, a language of three states that promises to carry more information, with less effort, and using less power. It's not a new idea, but its time may have finally come. To understand why ternary is so compelling, we have to look past the engineering and into the pure, elegant world of mathematics. Our binary system uses bits, zeros and ones. A ternary system uses trits, which can represent three values. The most mathematically beautiful version of this is called balanced ternary, which uses the values 1, 0, and +1. This isn't just an arbitrary choice. This symmetrical structure unlocks a remarkable level of efficiency. Imagine you're giving someone directions. In a binary world, you can only say, take a step forward, 1, or stay put, 0. To tell them to go backward, you need a separate instruction, a sign bit, which adds complexity and an extra step. In a balanced ternary world, you can say, step forward, +1, stay put, 0, or step backward, 1, in a single, fluid command. This elegance translates directly into computation. Certain arithmetic operations, like multiplication and division, become simpler and require fewer steps. The logic for handling negative numbers isn't an awkward add-on. It's baked right into the system's DNA. This translates into tangible physical benefits. Every time a transistor in a chip switches from 0 to 1 or 1 to 0, it consumes a tiny burst of power, and generates a tiny puff of heat. Fewer computational steps mean fewer switches. Less switching means less power consumption and less heat. Furthermore, each trit inherently carries more information than a bit. To be precise, a trit holds about 1.58 times the information of a bit, log 23. This means you can represent the same numbers using fewer trits than bits, leading to the potential for denser, more compact circuits. In essence, ternary computing is a way to think about calculation more naturally, a system where the mathematics and the physics align to create something more compact, more fluid, and fundamentally more energy efficient. It is like switching from a language with a small alphabet to one with a richer one. You can say the same things with fewer letters. Long before Silicon Valley became the center of the universe, on the other side of the Iron Curtain, a small team of Soviet scientists decided to challenge the binary consensus. In the late 1950s, at Moscow State University, a team led by Nikolai Brusentsov built the Setun, the world's first functional, mass-produced ternary computer. This wasn't some theoretical exercise. It was a real working machine, and by all accounts, it was brilliant. The Setun was built with ferrite cores and semiconductor diodes, components that were cheaper and more readily available in the Soviet Union than the complex transistors used in Western binary machines. It was remarkably power efficient, consuming far less energy than its American counterparts. Students and researchers who used it found it mathematically elegant and surprisingly easy to program for certain tasks. It was in many ways a superior piece of engineering. Its balanced ternary logic made it a natural fit for process control and academic research. About 50 Setun and later Setun 70 models were produced, a small but significant testament to the viability of the concept. So why aren't we all using descendants of the Setun today? The answer is a classic tale of a brilliant idea born in the wrong place at the wrong time. The Setun was an island. It had no ecosystem. While the West was building a massive, interconnected industry around binary, standardized languages like Fortran and COBOL, compatible hardware from multiple manufacturers, and a growing library of shared software, the Setun was alone. There was no robust industrial chain to manufacture its unique components at scale. There were no dedicated teams building compilers to bridge the gap between human programmers and the machine's ternary soul. It was a technical marvel that was defeated not by a better technology, but by the sheer, overwhelming force of the Western binary ecosystem. The Setun didn't fail. It was starved into obsolescence, a ghost of a possible future that flickered briefly and then died of isolation. The story of the Setun isn't just a historical curiosity. It's a powerful lesson in technological Darwinism. It proves that the best idea doesn't automatically win. The idea that wins is the one with the strongest army, an army of manufacturers, programmers, investors, and users all marching in the same direction. The Setun failed not because its logic was flawed, but because it lacked an industrial body. The world had already committed to the language of 0 and 1. This phenomenon is called technological inertia, and it's one of the most powerful forces in human history. Think about the QWERTY keyboard layout you're probably typing on. It was designed in the 1870s, specifically to slow down typists to prevent the keys on mechanical typewriters from jamming. Far more efficient layouts, like the Dvorak keyboard, have been invented since, proven to be faster and more ergonomic. Yet, QWERTY reigns supreme. Why? Because decades of infrastructure, every keyboard ever manufactured, every typing class ever taught, the muscle memory of billions of people, are built around it. The cost and chaos of switching would be astronomical. The binary system is QWERTY on a planetary scale. By the time the Setun proved the elegance of ternary, the binary ecosystem was already entrenched. Universities were churning out graduates who thought only in binary. Factories were tooled to produce binary components. The first killer applications, the software that convinces people to buy hardware, were all written in binary. To switch to ternary would have meant rewriting the entire digital playbook, re-educating a generation of engineers, and retooling a global manufacturing base. It was simply too late. The history of computing is a graveyard of brilliant ideas that were simply out of sync with their time. The Setun is a monument in that graveyard, a testament to the fact that victory often goes not to the most elegant, but to the first to scale to standardize and to convince the market that its way is the only way. So how do you actually build a ternary circuit? If a binary switch is either on or off, what does a three-state switch look like? The concept is surprisingly straightforward, though the execution is devilishly complex. At the electronic level, it's all about voltage. In a binary system, you have a single voltage threshold. Let S say anything above 2 volts is a 1, and anything below 2 volts is a 0. The gap between them is a buffer zone to absorb noise. A ternary system simply adds a second threshold. Imagine you have 2 lines drawn across your voltage range. Now you have 3 distinct, stable regions. The challenge, however, is what engineers call noise margin. With 2 thresholds instead of 1, the stable voltage windows for each state become narrower. The system becomes more sensitive to a host of physical gremlins, electrical noise from neighboring components, subtle variations in the manufacturing process, and most importantly, heat. As a chip heats up, its electrical properties change, causing these voltage thresholds to drift. If they drift too much, a bulb 1 might be misread as a 0, or a 0 as a 1. This is a catastrophic failure. The core engineering problem of ternary computing isn't the theory. It's the delicate, real-world balancing act of keeping those 3 states perfectly distinct and reliable under the immense stress of high-speed operation. It's a beautiful idea that constantly threatens to fall apart in the messy reality of physics. For decades, ternary computing was little more than a footnote in computer science textbooks. But now, in research labs around the world, it's being resurrected. Why? Because the very problems that made it difficult in the 1950s are being solved by 21st century science. The return of ternary is being powered by breakthroughs in material science and transistor design. Scientists are now experimenting with materials that go far beyond traditional silicon. Graphene, with its incredible electrical conductivity, and carbon nanotubes, with their unique quantum properties, offer new ways to build transistors that are more stable and less susceptible to thermal noise. These new materials can hold those delicate ternary voltage states with greater fidelity. We're seeing prototypes of memory chips that use 3 distinct physical levels, or plateaus, plateaus to store a trit rather than just 2. We're seeing new transistor geometries, like the FinFET or gate-all-around transistors currently entering mass production, which offer much better control over the flow of electricity, making it easier to define and hold multiple voltage states. The early results are incredibly promising. Lab demonstrations have shown ternary circuits that can perform specific calculations with significantly less energy and in fewer clock cycles, what AS, known as reduced logical depth, than their binary equivalents. This is no longer just a theoretical advantage. It's being measured in real, albeit experimental, hardware. But the history of the Setun looms large. A successful lab prototype is one thing. A technology that can be reliably and affordably manufactured by the billion is another entirely. The true test for the modern ternary revival won't be in a peer-reviewed paper, but on the factory floor. Can these new designs survive the transition from the pristine environment of a lab to the brutal, high-volume reality of industrial-scale production? Even if we stick with silicon, the material that built the modern world, the path for ternary is fraught with challenges. The very properties that make silicon so perfect for binary computing make it difficult for ternary. In a modern CPU, transistors are packed together at an almost atomic scale. The voltage windows are already incredibly narrow, and the amount of heat generated is immense. Trying to squeeze a third state into this already stressed environment is like trying to have a whispered conversation in the middle of a rock concert. The key problem is thermal drift. As a data center heats up under a heavy AI workload, the voltage thresholds in the chips begin to shift. In a binary system, there's enough of a buffer to handle this. But in a ternary system, that buffer is much smaller. A slight shift can cause a cascade of errors. To counteract this, a ternary chip would need a sophisticated system of active calibration. On-chip sensors would constantly monitor temperature and voltage levels, and control circuits would actively adjust the thresholds in real time to compensate. This is where the economic reality hits. These error correction and calibration circuits themselves consume power and take up precious space on the chip. The critical question becomes, do the efficiency gains from using ternary logic outweigh the energy and complexity costs of keeping it stable? If you save 15% of the power on the core calculation, but spend 20% more power on the support systems needed to make it work, you haven't just failed. You've gone backward. The challenge for modern ternary engineers isn't just to invent a perfect three-state circuit. It's to create one that is robust, reliable, and economically viable when produced in the millions and deployed in the chaotic, real-world conditions of a massive data center. So, where could this actually work? The most promising beachhead for Ternary's return isn't in your laptop or smartphone, but in the massive power-hungry brains of the cloud, AI data centers. Inside the specialized chips that train models like ChatGPT, there are a few specific, repetitive operations that consume a disproportionate amount of energy. One of the biggest culprits is the multiply-accumulate operation, a core component of processing the vast matrices of data known as tensors. This is where ternary can become a surgical weapon. By designing specialized blocks of ternary logic just for these high-intensity, energy-guzzling tasks, engineers are seeing real, measurable gains. Studies and simulations show that for these specific workloads, ternary circuits can achieve an efficiency improvement of anywhere from 8% to 18%. Now, on its own, a number like 18% might not sound revolutionary. But we have to think at the scale of a Google or an Amazon. These data centers perform not thousands, not millions, but billions or even trillions of these operations every single second, 24 hours a day. When you multiply that seemingly small percentage by that astronomical scale, the numbers become staggering. It represents hundreds of megawatts hour of energy saved per year for a single data center. That's enough electricity to power a small city. It's a direct reduction in a multi-million-dollar electricity bill and a significant cut in carbon footprint. The genius of this approach is that it doesn't require overthrowing the entire binary empire. Instead, ternary becomes a viable, strategic choice when applied with precision to the most painful energy bottlenecks in the system. It's not a revolution, it's an optimization. And in the world of hyperscale computing, optimization is everything. The most realistic path forward for ternary computing is not a dramatic overnight revolution, but a quiet, gradual infiltration. The future is hybrid. Imagine a standard binary microprocessor, but deep inside, tucked away in a corner of the silicon, is a specialized coprocessor, an accelerator block that thinks and works entirely in ternary. This block is designed for one specific job, like the tensor accumulation we just discussed, and it does that job with incredible efficiency. To the outside world, to the operating system, to the software, to the programmer, everything still looks binary. The main system communicates with this ternary module through a special translation layer. The compiler, the piece of software that turns human-readable code into machine instructions, is smart enough to know when to offload a specific task to the ternary block. It handles the conversion from binary to ternary on the way in and back to binary on the way out. From the user's perspective, absolutely nothing changes. Your applications run as they always have. You won't see a ternary mode button in your settings. But the impact is felt elsewhere. It's felt on the electricity bill of the data center. It's felt in the reduced heat output, which means less energy is needed for cooling. The ternary system enters not through the front door, proclaiming a new world order, but through the side door of the server room, disguised as a simple efficiency upgrade. This is how disruptive technologies often gain a foothold, not by demanding that we abandon everything we know, but by solving a painful problem so effectively and seamlessly that we barely notice it's there. It's evolution, not revolution. Even this clever, hybrid approach depends on one crucial factor: a stable, predictable, and affordable supply chain. A brilliant ternary accelerator is useless if you can't manufacture it reliably by the millions. This brings us back to the ghost of the Setun and the problem of industrial support. For ternary to succeed, it needs a foundation of materials and manufacturing processes that are just as robust as those for binary silicon. This is where the new generation of materials becomes so critical. Materials like graphene and carbon nanotubes aren't just scientific curiosities. They are potential solutions to the core physical problems of ternary computing. Their unique atomic structures could allow for the creation of transistors that maintain a much cleaner, more stable separation between those three voltage states, even at high temperatures. They could naturally reduce the electrical noise that plagues traditional silicon, making the delicate ternary logic inherently more reliable. They are the key to making ternary transistors predictable and uniform at a massive scale. But having a miracle material isn't enough. You need the entire industrial pipeline, the equipment to produce flawless graphene wafers, the techniques to etch circuits onto them with nanometer precision, and the testing methodologies to guarantee that every single chip off the line performs identically. Without standardization and a uniform, high-yield manufacturing process, the theoretical gains of a ternary chip will be devoured by high production costs and poor reliability. The future of ternary computing may be designed in physics labs, but it will be won or lost on the factory floor and in the lines of a cost analysis spreadsheet. Ultimately, the resurgence of ternary computing will be driven by the oldest and most powerful force in technology: money. In the new gold rush of artificial intelligence, energy efficiency has become a critical competitive advantage. Every watt of electricity an AI company saves is a dollar that can be reinvested into research, into hiring top talent, or simply into a healthier bottom line. Think about the cost of training a large language model. It can run into the tens of millions of dollars, and a huge chunk of that cost is pure electricity. A strategically placed ternary block that reduces the energy consumption of that training process by even a small percentage can translate into millions of dollars in savings. It means a company can afford to run more experiments, to iterate on its models more quickly, and to push the boundaries of AI further and faster than its competitors. The pressure for this kind of innovation is no longer coming from a handful of idealistic engineers in a lab. It's coming from the very top, from the CFOs and CEOs of the cloud computing giants and the AI startups who are paying the bills. They are demanding efficiency not as a feature, but as a fundamental requirement for investment. They are looking at their massive operational costs and seeing energy as the single biggest lever they can pull. In this high-stakes environment, ternary computing is no longer just an elegant mathematical theory. It's a potential business strategy, a tool for gaining a crucial economic edge in the most important technological race of our time. But here's a crucial lesson that goes beyond the hardware. A perfectly efficient piece of technology is useless if it's used in a wasteful and disorganized way. Having the most energy-efficient ternary hardware in the world won't save you a penny if your software workflows are a mess, your AI models are poorly optimized, and your prompts are inefficient. This is the difference between technical efficiency and operational efficiency. Technical efficiency is about the hardware, the watts per calculation, the speed of the chip. Operational efficiency is about the intelligence of the entire process. It's about writing clean, optimized code. It's about structuring your AI prompts to get the desired result with the minimum number of computational steps. It's about building automated pipelines that run smoothly without human intervention and wasted cycles. You can have the fastest car in the world, but if the driver is lost and keeps taking wrong turns, you'll never reach your destination efficiently. The true transformative gain comes when you combine the two. When you pair cutting-edge, energy-sipping ternary hardware with smart, streamlined operational processes. This integration is what turns a small percentage of energy savings into real, compounding growth. It's a holistic view of efficiency that understands that the machine is only one part of the equation. The human, the process, and the workflow are just as important. The ultimate goal isn't just to build a faster engine. It's to build a smarter car with a better driver and a clearer map. The binary system was the hero of the first digital age. It was the simple, reliable tool that took us from room-sized calculators to supercomputers in our pockets. It has earned its place in history. But the challenges of today, the insatiable energy demands of AI, the physical limits of silicon, are forcing us to look for new heroes. The ternary system, a ghost from computing's past, is returning not as a replacement, but as a specialist, called back into service at a time when its unique talent for efficiency has become a necessity. The revolution, if it comes, won't require us to burn down the old world. It will be about intelligently augmenting it, adopting the new where it makes the most sense. The future is not a war between binary and ternary. It's a strategic partnership. This isn't a matter of faith or belief in a superior technology. It's a cold, hard, strategic choice driven by physics and economics. And that brings the question back to us. This story isn't just about computers. It's about how we solve problems. For me, the lesson of the Setun and the return of Ternary is a reminder to never get so locked into one way of thinking that we dismiss other possibilities. It teaches us to constantly question if the tools we're using are still the best ones for the job, or if we're just using them out of habit and inertia. The advice I draw from this for our own lives is to always look for the third option. When faced with a binary choice, yes or no, this or that, ask yourself, is there a middle path? A hybrid solution? A different way of framing the problem that opens up new possibilities? Often, the most elegant and efficient solution isn't one of the two obvious choices, but something in between. So I leave you with this final question to think about. As your own personal and professional worlds become more complex when your limiting factor is energy or time or money, what part of your pipeline, your work, or even your life could benefit from thinking in 3 levels instead of just 2? Thank you for joining me on this journey into the hidden history and potential future of computing. Stay curious, stay questioning, and above all, stay healthy. And if you found this story thought-provoking and want to explore more ideas that challenge the world as we know it, please consider liking this video and subscribing to the channel. It helps us continue to bring these stories to light. We'll see you next time.